Hi Chem 101 students, and welcome back for our second and final lecture of this week. It's going to be about a theory called valence shell electron pair repulsion. And this is a very fancy name which basically says that bonds and lone pairs are made out of electrons. And electrons are negative and they don't like each other and they repel each other. And the fact that they do this helps us to determine what the shape of a molecule will be once we have drawn the Lewis structure. In addition, we're going to be getting these shapes so that next week we can determine if a molecule has a property called polarity. And the fact whether a molecule is polar or not polar is going to tell us a lot about its physical and chemical properties. But we're going to get to the molecular polarity next week. We're going to do this week is we're going to use the Lewis structure to determine the molecular geometry or the shape of the molecule using VSEPR. And then we're going to look at all of the bonds within the molecule and see if any of those bonds are polar. And a bond is polar when electrons spend more time close to one atom and less time close to another. And the result is that parts of the bond are more negative or more positive due to the greater density of electrons. So let's go right into the VSEPR, the valence shell electron pair repulsion model. And so this model is a very simple model, really. All it says is that because bonds and lone pairs are composed of electrons and have negative charge, they repel one another. And so the VSEPR model is basically a geometry type of model that just says that assuming that these bonds and lone pairs repel each other, they are going to want to be as far apart as possible in three-dimensional space. And so the model is assuming that they are, in fact, as far apart as possible in three-dimensional space. And the point of VSEPR is to determine the molecular geometry of the molecules. And that's going to be very important for determining their macroscopic properties. For example, you may not realize it yet, but you will by next week. The process that we're doing now, starting with drawing the Lewis structures, moving on to doing VSEPR to determine the geometry, and finally using the geometry to determine if a molecule is polar or not. This will ultimately explain to us why, for example, air is gaseous and we can easily move through it, but water is liquid. And it will also help to explain to us why other things like Vaseline, for example, are solid, and even why they're goopy solids as opposed to a very hard solid. So I promised near the beginning of the course that I'd finally be able to explain to you why all of these various substances have those kinds of properties. And we're finally to the point where we can discuss that now, which is very exciting. I hope you're as excited as I am to do this. That said, it's a very complex process to do this. So first of all, we're dealing with three-dimensional structures now, and visualizing things in 3 dimensions can be difficult. It's one of the great challenges of being a chemistry student. As you move further and further in chemistry, you are asked to be able to visualize 3-dimensional shapes in your mind in order to determine the properties and behaviors of a variety of molecules. So when we're drawing Lewis structures, for example, if we draw the Lewis structure of CH4 on a flat page, it's going to look like what you see on the left here. But the truth is, that does not look like the actual molecule at all. The real molecule is not 2-dimensional. You can't express it really on a 2-dimensional page. The 3-dimensional molecule looks something like this. And so the Lewis structure, that doesn't mean this Lewis structure is wrong. This Lewis structure is absolutely right. It's just that the Lewis structure does not necessarily represent the 3-dimensional structure of a molecule. It's not intended to. But what it can do is it can help you to determine what the three-dimensional structure of the molecule is by arranging what atoms are bonded to what other atoms. Now, although it's not really possible to use a Lewis structure to represent a three-dimensional shape like this one here, there is a modification of the Lewis structures that can help you to express the three-dimensional structure of a molecule on a two-dimensional page. And those are called wedge and dash Lewis structures. And so the wedge and dash Lewis structure of CH4 is written here. And it's written on the page to try to duplicate the three-dimensional structure that you see here. So you'll notice that this structure has a wedge here for this hydrogen. That's representing this hydrogen right here, which in the three-dimensional structure would be popping out of the page towards you. This hydrogen here is, its bond to the carbon is represented by a dashed line. And the dashed lines are supposed to represent bonds that are going into the page, away from you, behind the page. And so this hydrogen here is trying to represent this hydrogen in the background right here. Finally, lines that are flat are representing bonds that are in the same plane as the page, neither popping out nor going backwards into the page. That would be like these ones right here. These are both in the same plane of the page. They're neither popping backwards or popping forwards. That said, obviously, no matter how you draw it, there are challenges to visualizing something that is actually 3 dimensions on a 2-dimensional page. Even when you have a picture like this, that's not the same as having the shape in your hand and holding it and turning it around. What we can do, though, is we can simulate that. And a part of what you'll do for your discussion group this week is to look at a simulation for the shapes of these molecules and a simulation of VSEPR. So to apply VSEPR, it's going to take 5 types of things that you're going to have to do. Oh my gosh, now we're up to 9 steps, because the first step out of these 5 steps is that you have to draw a Lewis structure. So that will take up to 5 steps, either 4 or 5 steps. Then you look at the Lewis structure and you determine what we're going to call X. X is the number of atoms that are bonded to the center atom. Then you will look at the Lewis structure and you will determine E. E is the number of lone pairs attached to the central atom. Very important here is that we are focusing on the center atom. The shape is built around the center atom. If there's more than one center atom, then we apply the same process to every atom that is in between other atoms. So if there's more than one center atom, we repeat these remaining steps here, not drawing a Lewis structure, obviously that will already be drawn, but we repeat all these VSEPR steps for every central atom that there is. If there's only one center atom, we only have to do it once. But if there's more than one center atom, we may have to do it multiple times. Then you calculate X plus E. This is the number of total electron groups around the center atom. And so this is the number of bonds, whether they be double or triple, they all count as one electron group. That's very, very important here. Notice that X is the number of atoms bonded. It's not the number of bonds. And so a double or a triple bond still counts as only one electron group because all the electrons are there in one place. And so do lone pairs. So X plus E is the number of bonded atoms plus the number of lone pairs, which together gives us the number of electron groups that would repel one another in the VSEPR model. Finally, we use X plus E and E, the number of lone pairs on the center atom, to determine the molecular geometry based on the maximum spacing between all electron groups. And so this could be, determined using your mind. And in fact, the simulation I'm going to have you do really shows how you could add things on and take things off and get the different shapes. But the results are this here. So we calculate X plus E, and the vertical column here represents X plus E. And remember, X is the number of atoms bonded to the center atom. E is the number of lone pairs on the center atom. And then this is E, and the geometry is listed here. So there are some funny names for these geometries, but here they are. So if we were drawing the Lewis structure of CO2, which you are going to do, but this is the Lewis structure of CO2 right here. So if we look at this structure here, we can see that the number of bonded atoms is 2. So we have 2 oxygens bonded to the carbon. Carbon is the center atom. It has 2 atoms bonded to it. So X equals 2. X does not equal 4. X is not the number of bonds. There are 4 bonds, a double bond here and a double bond here, 4 total bonds. But that is not what X is. X is the number of atoms bonded to the center atom. That is 2 oxygens bonded to the center atom. Basically, each double or triple bond counts as 1 for the X. It doesn't count as multiples. So then E is the number of lone pairs on the center atom. Now there are lone pairs here on the oxygens, but that's not what we're counting. We're counting the lone pairs on the carbon. There are no lone pairs on the carbon. So E equals 0 here. And when X equals 2, so X plus E is 2, and E equals 0, you get a linear shape. The reason why it's linear is just based on the idea of VSEPR, valence shell electron pair repulsion. We have 2 electron groups. One of the electron groups is this double bond here. The other electron group is this double bond here. Those electron groups are going to want to position themselves such that they are as far apart as possible from one another. That means going on exactly opposite sides. And so you can see it here. They're on exactly opposite sides of the center carbon atom. Here, these red ones represent the oxygens. The black one represents the carbon. And the angle between this bond is 180 degrees here. And so that's what happens when you have X is 2 electron groups, and no lone pairs on the center atom. And again, it's all about the center atom because the shape is built around this center atom. Now earlier, we drew the Lewis structure for formaldehyde here. And this is the Lewis structure we got. Again, it doesn't matter the orientation. We could flip this any which way. Real molecules, as you'll see on the simulation, they can flip all around. They're always flipping around. So it doesn't matter what the direction of everything is. It matters that the Lewis structure is bonded correctly, right number of valence electrons, right covalence numbers. Everyone has an octet. And so this is formaldehyde. So if we're looking at the X's and the E's, remember, X is not the number of bonds on the center atom. It's the number of atoms bonded to the center atom. There are 3 atoms bonded to the center atom, 2 hydrogens and 1 oxygen. So X equals 3 here. X equals 3. Now E is the number of lone pairs on the center atom. Oxygen has lone pairs, but that's not what we're looking at. We're looking at the center atom, carbon. It has no lone pairs. So there are 3 electron groups. This bond, and then this double bond. Those electron groups, according to VSEPR, are going to want to position themselves as far apart in 3-dimensional space as possible. And the way that works out is in a flat triangle like this, with a funny name, trigonal planar. Trigonal is like triangular. Planar means flat. But why didn't they just call it flat triangle? I don't know. That would have been easier. But instead, you have to remember this term, trigonal planar, which means flat triangle. And the angle between the bonds here is 120 degrees. These ones are pretty easy to figure out because all around is 360, right? So here we have 180, 180, that's 360. Here it's 120 degrees, it's 120, 120, and 120. So that all adds up to 360. And so that is a trigonal planar molecule. Now here we have the molecule NOF. We did a similar one, POF. It works out to the same if we had a P here because this phosphorus is in the same group as nitrogen, so it ends up looking exactly the same. So for this one, we have nitrogen in the middle. It has two atoms bonded to it, oxygen and fluorine here. So here, X equals 2. Two atoms bonded to the nitrogen. And E, the number of lone pairs on the center atom, the nitrogen, is 1. X is 2 and E is 1. When X is 2 and E is 1, you end up with this shape bent. And so it has 3 electron groups still. X plus E equals 3. Notice X plus E equals 3. 2 plus 1 is 3. However, one of those groups this time is a lone pair instead of a bond, a double bond, or single bond. So although this lone pair does take up space and does repel the electrons that are in the bonds, it's not included in the shape. It's like a triangular, it's a flat triangle shape except no top part here. So instead it's like this. This is the shape. It's called bent or angular. The angle is still about 120 degrees. It will be slightly smaller than 120 degrees. That's why I put the little tilde here, because lone pairs tend to take up a little bit more space than regular bonds. So this squeezes this angle down just a little bit. But you don't need to know the exact angles. When you do the simulation, you'll see that that it does tell you the exact angles for some molecules. So it would be about 120, but it might be slightly smaller. So you'll be able to check that out for a few pre-built molecules, which is pretty interesting. Next, we have this horizontal row here. This is where X plus E is 4. So here was X plus E is 3. Here because X was 3 and E was 0, or because X was 2 and E was 1. And so here X plus E was 3, but E was 0. Here X plus E is 3, but E is 1. And so that's why it's right here. Next, we have a situation where X plus E is 4, but E is 0. And that is with CH4. So here the carbon is bonded to 4 hydrogens, and I've shown this with the wedge dash type structure here. So for CH4, X equals 4 because there are 4 atoms bonded to the center atom. Hydrogen, 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 hydrogen. Okay, 4 atoms bonded to the center atom. But E is 0 because there's no lone pairs on the center atom. And so this is the first shape that's not flat out of all of these. So if these 4 bonds, the electrons in these 4 bonds, want to repel each other so that they are all as far apart as they can be from one another, they're going to make a shape called a tetrahedron. So this is called tetrahedral. And the angle between all of these bonds is going to be 109.5 degrees here. And so that's what happens if you have X plus E is 4, because X is 4 and E is 0. E is 0 here. Now an example of a molecule with the shape trigonal pyramidal. Again, why the funny name? It's because look at this shape here. It's triangular on the base, but it's like a pyramid. It's like a tripod. So trigonal pyramidal, triangular pyramid. And so this is what will happen if X plus E is 4, but E is 1. So here's the Lewis structure for NH3. In NH3, X, the number of atoms bonded to nitrogen, is 3. There are 3 hydrogens bonded to nitrogen. And E, the number of lone pairs, is 1. There's 1 lone pair on the nitrogen. And so X plus E is 4 and E is 1. So when X plus E is 4 and E is 1, you get the shape trigonal pyramidal. And the bond angles are still about 109.5, but notice it's like a tetrahedron, but the top isn't there because the top is a lone pair instead. And so you get, and because the lone pairs take up a little extra space, you get bond angles that are a little bit less than 109.5. But the theoretical bond angle is 109.5. It's just the lone pairs take up a little bit more space and push the other bonds inward a little bit more, reducing that angle just a bit. Finally, if X is 2 and E is 2, that's the case here for water, H2O. So the Lewis structure for water is here. In water, oxygen is the center atom, and the number of atoms bonded to the oxygen is 2 hydrogens. So X equals 2. And I'm kind of in the way here. Now for the number of lone pairs on the center atom, we have 2 lone pairs on the center atom, oxygen. And so E here equals 2. So X plus E is 4, and E is 2. And this gives us a bent geometry like this. So again, the angle is still 109.5, but now these two spots up here are taken up by lone pairs, and that causes the molecule to be in this bent shape here. And so that is an explanation for VSEPR. Now, it is possible for some atoms to exceed the octet rule and make 5 bonds or 6 bonds. However, I do not go through that. I'm not going to make you responsible for that. Your book does go into exceptions where there are exceptions to the octet rule. You don't have to do anything with the exceptions to the octet rule. If you're interested in them, you could look at them, but I'm not going to test you on that. I'll leave that for your next chemistry class if you take one. Almost all biological molecules, they stop here at 4 bonds. One exception, phosphorus makes 5 bonds in DNA, which we'll look at, but for the most part, they follow the covalence numbers and make and max out in an octet. But anyway, this is how you apply VSEPR. So just going back to the rules, to the steps again, you got to have the Lewis structure first. So first you got to do all that, drawing the Lewis structure. Then determine the number of atoms bonded to the center atom, which is X. Determine the number of lone pairs attached to the center atom, that is E. Add up X plus E, and then using X plus E and E and this table, determine the geometries, which are written here. Now, the PhET website, where we did one of our labs before, has a great simulation of molecular shapes. And so I've made that the topic of your discussion group this week. What I'd like you to do is go into that simulation, simulate a molecule that you've drawn a Lewis structure for, and then say what the molecule is and say a sentence or two about what you did, and then upload a picture, a screenshot like I did here for the simulation that you did. So it applies VSEPR to create molecular geometries, and the cool part is you can tug on the bonds in the atoms and see how the electron pairs repel one another. I'm going to try to open that. I'll just go there. Maybe if I go like that, there we go. Okay, and so you can go to model, and model lets you build your own, and it's cool, you can tug these around. Now this will give you molecular geometry, so this one's linear, also electron geometry. I don't really say much about electron geometry, that's just including the lone pairs. And you can now add whatever you want, like you can have, so here we have 2 atoms bonded, no lone pairs, so it's linear. X is 2, E is 0. We can add a bond. So here X is 3, E is 0. We could have even made this a double bond if we like. X is 3, E is 0, so that's like the formaldehyde. And again, you can pull on these and you'll notice they repel one another. And molecules are jiggling like this all the time. Real molecules are always jiggling and wiggling. But their average shape is like this because that allows these to be as far apart from one another as possible. You can also show bond angles here, so you can wiggle these around like this. You can throw in a lone pair. I'm gonna get rid of this. So here we got like the NH3. So see how the lone pair takes up some space. Now in the idealized model, every angle is still 109.5 because x plus e is 4 and e is 1. So like if I take off the lone pair and put a bond, okay, 109.5, right? And I can wiggle this around. If I replace the bond with a lone pair, still 109.5. You can also go to, and you can see they tell you the shape here, trigonal pyramidal. A really, really cool simulation. You can choose to show the lone pairs or not. So this is the reason why this molecule has this trigonal pyramidal shape, is because the lone pair takes up some space up here, but it's not included in the name of the shape. So you can see that if you put on electron geometry, it shows tetrahedral. That's because it's including the lone pair in the shape. But when I ask you for what is geometry, I'm talking about the geometry of the molecule, and that is, oops, lone pair, and that is you know, without the shape without the lone pair. Now you can also click down here and go to real molecules. And this will show you what happens to the bond angles when you have real molecules. So this is water, the geometry is bent, and you can see the lone pairs are taking up space. You can either show them or not, but either way they take up space, right? They're repelling the electrons that are in the bond. You can rotate this around to get it. If you click outside the shape, it will rotate it around. And you can show the bond angle. So you can see that in the real molecule, the bond angle is actually 104.5, slightly less than 109.5. So in the model, every bond is 109.5. But in real life, because the lone pairs take up a little extra space, that bond angle gets squished down a little bit to 104.5. Let's look at this for NH3. So it's the same thing here. It has 4 electron groups. X plus E is 4. So in the model, the perfect model, all the angles are 109.5, but realistically the lone pair does take a little bit of extra space, and so the real bond angles in NH3 are a little bit less than 109.5, 107. It's a really cool little thing you can play around. I really like that you can pull and push on the bonds, because it shows you that these electron pairs are repelling one another. You can wiggle them around. They're always wiggling anyway, but they're going to go back to the situation where they're all as far spaced apart as they can be, because that's what VSEPR is. So really cool simulation there. Go into that and use that to do a little simulation for a molecule yourself and post it up on the discussion board for this week. So let's do a few examples of using VSEPR to determine molecular geometry, where in these examples we have to go through the whole process here of drawing a Lewis structure and everything. So step 1 is we got to draw a Lewis structure. So SF2, count the valence electrons, get the covalence number. That's step 1 and 2. We have 1 sulfur, and sulfur is in group 6. We have 1 fluorine, and fluorine is in group 7, so 7 valence electrons. Valence electrons total from the sulfur would be 1 times 6. We got not 1 fluorine, we got 2 fluorines right here. We have 2 fluorines times 7, and we did this one in the previous lecture, so I'm going to go through it pretty quickly. That's 14. We had 20 altogether. Sulfur starts with 6 valence electrons, needs 2 more to have 8. Fluorine starts with 7 valence electrons, needs 1 more to have 8. Draw the skeleton structure here. Put the S in the middle. Put the F's on the outside. The way you draw this doesn't matter. I just happen to be able to get the shape very quickly in my mind because I've done this lots of times, and you will be able to do that too eventually if you do these enough times. Okay, then we put electrons on the outside atoms first. As lone pairs. And then right now we have 16 down, we have 4 more left, and that is 20. We have 20 valence electrons. the covalence numbers, 2 bonds for the sulfur, 1 bond for each fluorine, and everybody has an octet. And so in this molecule, X equals the number of atoms bonded to sulfur is 2, and E here is the number of lone pairs on the center atom. These ones right here. These ones don't count. They have to be on the center atom. So the sulfur is in the center. It's bonded to 2 atoms, so X is 2. And it has 2 lone pairs, so E is 2. So X plus E equals 4, and E equals 2. So when X plus E is 4, and E is 2, that is a bent or angular shape. So we'll say bent. All right. Now this one we didn't do it in the last lecture, so I'm going to do this one a little bit more slowly. NCl3, valence electrons, covalence number. We have 1 nitrogen and we have 3 chlorines. Nitrogen is in group 5. And chlorine is in group 7. So nitrogen has 5 valence electrons, chlorine has 7. 5, 7. So 1 nitrogen with 5 valence electrons, that's 5 total valence electrons. 3 chlorines, each with 7 valence electrons. That is 3 times 7, 21 valence electrons for a total of 26. Since a nitrogen starts with 5 valence electrons, it needs 3 more to have 8, so its covalence number is 3. Since each chlorine starts with 7 valence electrons, they need 1 more to have 8, covalence number is 1. So when we draw the skeleton, the nitrogen's going to go in the middle, and the chlorines are going to go around it. So that's step 3, we drew a skeleton. Next, we're going to put additional lone pairs as electrons around the outside atoms until they have an octet. So there's 2 in the bond there, 4, 6, 8. 2 in the bond, 4, 6, 8. Then 2 in the bond here, 4, 6, 8. Now we should check to see how many electrons we put down so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've put down 24, so we have 2 left. And those last 2 are going to go on the center atom, that is the nitrogen. And now each chlorine atom has an or let's count the total number of valence electrons. We just counted them. There are 26. In terms of covalence number, the nitrogen, is it making 3 bonds? 1, 2, 3. Yes. Is the chlorine making 1 bond? Each chlorine is making 1 bond. Yes. Does everybody have an octet? 2, 4, 6, 8 around each chlorine. And for the nitrogen, 2 in the lone pair, and 4, 6, 8. The rest in the bonds. So in this one, the center atom is the nitrogen, okay? It's all about the center atom. So X here, the number of atoms bonded to the nitrogen is 3. E, the number of lone pairs on the center atom is 1. So X plus E equals 4. And E equals 1. So X plus E is 4, and E is 1. This will have a trigonal pyramidal geometry. Trigonal pyramidal geometry. And also we could label the bond angles here. Bond angles here is about 109.5 because x plus e is 4. Here also x plus e is 4, and so bond angles are about 1.5 degrees. Finally, I wanted to give you at least one with more than one center atom here. And so let's do this one. I'm going to use my pair right here. So valence electrons, valence numbers. Okay. And so we got here 2 carbons. We've got 1 hydrogen, and we've got 3 fluorines. And carbon is in group 4. Hydrogen is in group 1, so 1 valence electron. Chlorine is in group 7, 7 valence electron. So 4 valence electrons for chlorine, 1 for hydrogen, for carbon rather, 7 for chlorine. So 2 carbons times 4 valence electrons each, that's 8. 1 hydrogen, 1 valence electron, that's 1. 3 chlorines times 7 valence electrons each, that is 21, for a total of 30 valence electrons altogether. And carbon has 4 valence electrons, needs 4 more to have 8. Hydrogen, always covalence number 1. Chlorine, 7 valence electrons, needs 1 more to have 8. Valence number 1. So the carbon goes in the middle, and again, like we saw in the last lecture, it's possible that we will have more than one center atom. If we've got, for example, both these carbons have covalence number 4, they might both be in the middle. This happens a lot for carbon. So I'll just write the carbons together in the middle, and then I'll write the other atoms around it. And this is where it can be difficult to decide where you're going to put them, right? I could put everything on one carbon, but if I put 3 chlorines and the 1 hydrogen on one carbon, it will be very difficult to get 4 bonds on the other carbon. The other carbon does need 4 bonds. So I'm probably best off spreading them out. So I have 1 hydrogen, I'll just put that right here. Then I have 3 chlorines, so I'll put a chlorine right here, a chlorine right here, and a chlorine right here. So when in doubt, spread them out, you know. That way, especially if you have an atom like carbon that needs to make 4 bonds, it doesn't even have 4 bonds yet. So we're going to try to make it so we can get each carbon as close as possible to 4 bonds. Now we start to drop lone pairs on the outside atoms first, but remember, hydrogen never gets any lone pairs. It'll make me very sad if I see lone pairs on hydrogens. Don't do it, don't do it. It's done. Hydrogen fills up with 2. But the chlorines can have 8. So they're starting with 2 in the bond, and so if we give them 6 more, they will have 8. So this one has 8 now. Let's give this one 6 more as lone pairs. It has 8. Let's give this one 6 more as lone pairs. Now it has 8. Okay. And so now let's count up how many we've put down. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So we've actually put down 28 electrons. We've got 2 left. So we can put the last 2 on either one of the carbons. But the problem is the other carbon doesn't have an octet, and neither of them are making 4 bonds. So now that we've run out of electrons and we have an atom that doesn't have an octet, now we use step 5. So we're going to erase that lone pair from the carbon, and we're going to make it instead a double bond. Okay. And so now we have 2 center atoms. So here's what we do when we have 2 center atoms. We take the same process and we apply it to both of the center atoms. Okay, so we're going to do it for this center atom. So this is a center atom, and we're going to do it for this center atom. A center atom means any atom that is between other atoms, and both of these carbons are between other atoms. So for this carbon, X, the number of atoms bonded to it, equals 3. There are 3 atoms bonded to this carbon. 1, 2, 3. E, the number of lone pairs on this carbon, is 0. No lone pairs. So X plus E is 3, and E is 0. So when X plus, and so let's do it again for this one now. Okay, the number of atoms bonded to this carbon is 1 carbon here, 2, 3. 2 chlorines, 1 carbon. There are 3 atoms bonded to this other carbon. The number of lone pairs on that carbon is 0. And X plus E equals 3. So both of these carbons are, it turns out, going to have the same geometry. So they're both going to be X plus E is 3 and E is 0. Let's see what geometry that is. X plus E is 3 and E is 0. This is trigonal planar. So these are both going to be trigonal planar. But you do have to do the whole process for each center atom if you have more than one center atom. Whoops, and I'm blocking it. Dang it. Okay. Kind of blocked what I was saying there, but there it is, you guys. X equals 3, E equals 0. Man, my head got in the way. I should have moved it over a little bit. But you guys get the idea. You can kind of see through my head anyway a little bit. Okay. So now we've got the next piece of the puzzle. So we've got the Lewis structure, which allows us to get the molecular geometry. But we're building up to something. We're going to use this molecular geometry along with another property, the polarity of bonds that are within the molecule. And ultimately, between the two of those, next week, we'll use those to decide if molecules are polar or not. So you can see this is kind of an involved process, right? So let's go on to the next topic, which is bond polarity. You have polarity in bonds when you have unequal sharing of electrons. So what you do is you look at a property called the electronegativity. And the electronegativity is a measurement of how hard a type of atom pulls on electrons within a covalent bond. If the difference in electronegativity is less than 3.5, or the difference in pull, we'll say that the bond is nonpolar, or is not significantly polar, but we just say nonpolar. The greater the difference in the electronegativities, the more polar the bond is. And then if we have polar bonds arranged in a particular geometry in a molecule, we can end up with a molecule overall that's polar. But again, we're going to move on to polar molecules next week. So here are the electronegativities. Now I did give you an electronegativity chart earlier, but I did update this electronegativity chart with more modern values. I had a little bit old values on there. Either way, you should be able to use those values to determine if a bond is polar or not. But I modernized the values a little bit, which were slightly different from one another here. So when we're writing the formulas, remember when we saw this one before, when we write formulas, we always write the formula with the atom with the lower electronegativity first and the higher electronegativity second. But also, what we really use these electronegativities for is to determine the polarity of bonds. And so we're going to take these values, we're going to compare them for two atoms that are bonded and figure out if a bond is polar or not. So for example, we look at these bonds here. Which bond is the most polar? So first of all, we're going to need the electronegativity values here. Whoops. So let's go back and look at them. So let's see what the electronegativity for carbon is. For carbon, it is 2.5. 2.5. And for oxygen, it is 3.5. And for nitrogen, it is 3.0. 3.5 for oxygen, 3.0 for nitrogen. 0.5 for oxygen, 2.5 for carbon, and 3.0 for nitrogen. So to decide which bond is the most polar, what we do is we take the difference between these. So it's going to be 3.5 for the oxygen. You just take the bigger one minus the smaller one. Minus 2.5 for the carbon. So here the electronegativity difference is 1.0. This is definitely a polar bond because the electronegativity difference is at least 0.5. So this is a polar bond. For the next one, oxygen is 3.5. For nitrogen, it's 3.0. And so the difference here is 0.5. So this bond is also polar, but it's less polar than the carbon-oxygen bond. Finally, for nitrogen has the higher of the two here, 3.0 electronegativity for nitrogen, 2.5 electronegativity for carbon. So the difference is 0.5. This bond is also polar, but the most polar bond is the carbon-oxygen bond. One note about electronegativities too, in the past we did talk about the effective nuclear charge, or the strength of the pull of atoms on electrons, and we said that it's highest near the top right of the periodic table where fluorine is. And you can see that reflected in the electronegativity values too. Fluorine has the highest electronegativity value, and they get smaller as you go down and to the left on the periodic table. So regarding these, so these are just one bond that might be in a molecule. When you're looking at a molecule, you want to analyze all of the different bonds that are in the molecule to see if any of them are polar. Notice we always did the largest one minus the smallest one. It's because we're trying to just get the absolute value of the difference. What we do about thinking about what's going on with the polarity of the bond is we notice that oxygen has the higher electronegativity at 3.5, carbon the lower electronegativity. So often an arrow like this with a cross at the end is written next to a bond like this. And then partial charges may also be written. A partial charge is often indicated with a lowercase delta with a negative sign for the negative charge. The oxygen here is partially negative because it pulls on electrons in the bond harder. So it has more electrons around the oxygen. So the oxygen area of this bond is more negative, and the carbon area would be more positive because it would be lacking in electrons. In this, the way this is written here, the oxygen has higher electronegativity than the nitrogen, so it would be like this as well. And here the carbon is 3.0 in electronegativity, the carbon is 2.5, so it would be like this. So in all of these, the electrons are being pulled more to the atom on the right side, and they're being pulled away from the atom on the left. And all of these are pretty polar bonds, but carbon-oxygen is by far more polar than the other two. So non-polar it means that when you have a non-polar bond, it means the electrons are shared equally. So if you have two of the same atom bonded to one another, they're going to share the electrons equally. Neither one will pull on the electron any harder than the other. But polar is unequal sharing. So when one atom has a higher electronegativity than the other and is pulling electrons its way. This can be represented with electron clouds like this here. So if we have and electron clouds are like this, are a way of describing the relative electron density, or the place where the electrons are spending more of their time. So in a nonpolar molecule, like for example, let's say we had F2. In a nonpolar molecule like this, the electrons are shared equally between the atoms. So there's equal electron density on one side of the molecule compared to the other. So even though fluorine pulls very hard on electrons, it pulls the hardest out of anybody. But if it's pulling against another fluorine, they're like two buff guys pulling against one another. Neither one is going to win that tug of war for electrons. And so the electrons will be evenly distributed between the two atoms. However, if we have a polar bond, like for example here, let's say the left one was a fluorine, so very hard electron polar, but the right one was a hydrogen. So for the fluorine, by the way, it has an electronegativity of 4.0, and for hydrogen it's 2.2. And so the fluorine pulls electrons very strongly in its direction. And so in this molecule, the electrons are pulled in the leftward direction. And as an electron cloud, that would be shown like this, with a larger cloud around the fluorine with more electron density and a smaller cloud around the hydrogen. Finally, this says to draw the Lewis structures of each of these and determine the polarity of all of the bonds. So again, notice that the first thing that we always have to do is to draw the Lewis structure, even if we just want to know what bonds there are. The point of drawing the Lewis structure is to tell us what atom is bonded to what other atom. And so we will need to draw the Lewis structure to do that. And so here, let's draw the Lewis structure, or to know that rather, know which atom is bonded to another. So anyway, let's draw the Lewis structure here. So we got to count the valence electrons. That's always the first step. We got to determine the covalence numbers. We've got one carbon in this molecule. We've got one oxygen, and we got two bromines. Carbon is group 4 in the periodic table, so 4 valence electrons. Oxygen is group 6 on the periodic table, and bromine is group 7 valence electrons. So carbon group 4, oxygen group 6, bromine group 7. So we have one carbon with 4 valence electrons, we have one oxygen with 6, we've got two bromines each with 7, so that's a total of 14, and so all together we've got 24 valence electrons. Okay. And the covalence number is however many more the atom would need to have 8. So each carbon would need 4 more to have 8. Each oxygen would need 2 more. And the bromine would need 1 more to have 8. Because each bromine starts with 7. Okay. So we draw a skeleton with the atom with the highest covalence number in the middle. We draw the other atoms around it. 1 oxygen, 2 bromines. We drop the electrons as lone pairs around the outside atoms first, so they have an octet. So that gives bromine an octet, 6 in the lone pairs, 2 in the bond. We'll do the same for this bromine. And then finally we'll do the same for oxygen. Give it an octet. So now they all have 8 around them, but carbon doesn't have an octet. Let's see how many electrons we have left. So we have 24 available. We have dropped 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We are out of electrons, but carbon does not have an octet. So we're going to have to share from either the bromine or the oxygen to make a double bond. So before we decide which one's going to make a double bond, we should look at the covalence numbers and see which one of these would want to make 2 bonds. Not the bromine. Bromine only wants to make 1 bond, so it shouldn't make a double bond. It's going to be the oxygen. So we're going to erase one of the lone pairs and instead make it a second bond. Okay. And so now we can figure out the shape of this. The shape happens to be trigonal planar. But what we were asked to do is determine what bonds are in there and what are the polarity of the bonds. So this molecule has a carbon oxygen to carbon bond in it, and it has 2 bromine to carbon bonds in it. So there are 2 types of bonds here. It doesn't matter if they're single or double bond. All we care about is what atoms are bonded to what other atoms. Oxygen is bonded to carbon, and bromine is bonded to carbon. Okay, so now we can figure out if these bonds are polar or not. we're going to have to look at the electronegativities. So oxygen, carbon, and bromine. Oxygen is 3.5, carbon is 2.5, and bromine is 3.0. So oxygen was 3.5, carbon was 2.5, and bromine was 3.0. Carbon 2.5. So the electronegativity difference here is 3.5 minus 2.5. This is electronegativity difference of 1.0. This is a polar bond. The oxygen-carbon bond. And then for this one, it's 3.0 minus 2.5 for bromine and carbon. That is 0.5. So the bromine-carbon bond is also a polar bond. Now for this one, SiI2, I'm going to have to write this a little bit lower. So Si2. Valence electrons, valence number. We got 1 sulfur, 2 iodines. So sulfur is group 6, 6 valence electrons. Iodine is group 7, 7 valence electrons. We have so 1 times 6 for the sulfur, 6 valence electrons. 2 times 7 for the iodines, 14. That is 20 electrons. And then sulfur is group 6. Starts with 6 valence electrons, needs 2 more to have 8. Iodine is group 7, starts with 7 valence electrons. Each iodine needs 1 more to have 8. We draw the skeleton with the highest covalence number atom in the middle. That will be sulfur. And then the other atoms attached to it, we put down lone pairs around the outside atoms till they have an octet. Okay, this iodine has an octet. It's 2, 4, 6, 8. That and that. And that will give us 20 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now, you may have been able to figure out that the only bond in this is sulfur to iodine anyway. You might have been able to figure out that quicker, but if you draw the Lewis structure, you guarantee you've figured it out. So the bond is between sulfur and iodine. So we're going to need the electronegativities for sulfur and iodine. And for sulfur, it's 2.6. For iodine, it's 2.7. So 2.6 for sulfur, 2.7 for iodine. And so the difference here is 2.7 minus 2.6, 0.1. So sulfur iodine bonds are nonpolar bonds. Then for the last one, I actually drew that structure earlier in this lecture, so I'll just write it back up. So what kind of bonds do we have here? Well, we got 3 types of bonds in this molecule. So in the first molecule, we had oxygen bonded to carbon. We also had bromine bonded to carbon. Those were our 2 types of bonds. In the second molecule, the only type of bond we had was silicon bonded to iodine. But in this molecule, we have a carbon bonded to a hydrogen. We have a carbon bonded to a chlorine 3 times. And we also have carbon bonded to carbon. So there are 3 different types of bonds. And we want to know for each of these 3 types of bonds, are they polar or not? We have a carbon we have a carbon to hydrogen bond. We have a carbon to carbon bond, and we have 3 carbon to chlorine bonds. So we're going to need the electronegativities for each of these. So carbon, hydrogen, chlorine. For carbon, it is 2.5. For hydrogen, it is 2.2. And for chlorine, it is 3.2. (2.5) for carbon, 2.1 or 2 for hydrogen, and for chlorine it is there was 3.2. All right. So the difference for carbon and hydrogen, it's going to be 2.5 minus 2.2, that is 0.3. This is a non-polar bond, the carbon-hydrogen bond. For the carbon-carbon, clearly it's non-polar. I mean, you could subtract it if you want. 2.5 for carbon, 2.5 for carbon, 2.5. So that's 0.0. Oh man, I'm writing behind my head again. Dang it. I'm just going to do it over here. I meant not to write behind my head. Okay, 2.5 minus 2.2, that difference is 0.3. So that's not a polar bond. For carbon, it's 2.5 minus 2.5 for the carbon-carbon bond, that's 0. And then for the carbon-chlorine, it's 3.2 for the chlorine minus 2.5 for the carbon, that is 0.7. So this bond is not polar. The carbon-carbon bond is not polar. And the carbon-chlorine bond is polar. So if you have more than one type of bond in your molecule, you need to figure out what bonds are in there and then figure out if what each of their polarities is. Finally, now that we've got all those preliminaries set, when we start next week, we're going to look at a molecule like any of these molecules. We're going to do our 5 steps to draw a Lewis structure like we just did. We're going to apply VSEPR to determine the geometry. We're going to analyze the bonds in the molecule and figure out if any of them are polar. And we're going to use all of that information to decide whether the molecule in its entirety is polar or not. And we'll begin to talk more about that next week. Happy studying. I kind of combined my 2 lectures into 2 longish lectures this week instead of 3 shorter lectures because I couldn't figure out a real way to split it into 3. But happy studying, and I'll see you guys in office hours. See you next time.